Okay, let's start studying concurrency. So first things first, let's look at some logistics. So here is the homepage, github.com/kaist-cp/this, and I think that you should read this repository very carefully. It contains a README and it contains a lot of information you should know to finish this course. All the announcements and questions should be in the issue tracker. So please watch the repository so that all the new announcements and questions will be automatically delivered to your email account. And there will be no official office hours, and we require you to ask questions in the issue tracker first. So you go to the repository and then see what's going on there. And if you have any questions, please create a new issue. And also, for each session, we require you to submit quiz answers so that we can be quite sure that you actually saw the video. So I'm going to ask a few questions on the videos that is corresponding to each session, and you're going to submit the answers to this site, gg.kaist.ac.kr. So your account has been already created, and please go to the repository and the README and the announcements. Also, I want you to sign the honor code, which is pretty standard among the School of Computing. It is basically mandating you to stick to the integrity rule of the academia. So it is fairly standard, so please read it and please sign the honor code in this URL. Okay, so basically I want you to read the homepage carefully and do some things for attendance and honor code. And next, I'm going to explain a little bit about grading. And for this course, homework will be very important, and it will constitute about 60% of the entire credits. So if you miss homework, so you will not get a good grade. So please do the homework on time. And furthermore, we will have midterm and final exams, but due to the COVID-19 situation, where I'm still not sure whether we are going to actually take midterm or final exams. So the grading scheme may change a little bit depending on the COVID-19 situations. Also, I'm going to look at some attendance results. So for each session, I said that you should go to this site and submit the quiz answers. And if you attended most of the courses or you answered most of the quizzes for each session, then you're good. But if you miss a lot of quizzes, then it'll be a problem. So I'm not still decided whether how to apply this attendance into grading. But please please watch the videos and go to this site and submit the quiz answers as much as possible. Okay, here is some logistics, and if you have any questions, go to the homepage and read the README carefully. And if you still have more questions, please ask questions in the issue tracker. And let me start with the introduction on the concurrency. So it is one of the famous scene in this 21st century. It is the Badook match with AlphaGo and Isedo, and it's probably the beginning of the first session. So he's going to lay the stone and here. And as all of you know, AlphaGo won 4-1. It is a one-sided win over the Grandmaster Isedo. So everyone was shocked. Most of the people thought that Isedo will win because AI is so crude at the time, and people thought that Isedo is a really great Grandmaster of Badook, and it cannot be beaten. And I also thought that E et al. Will win because I know that AI will do something good, but I still thought that AlphaGo will not be that good. But as contrary to what most of the people thought, AlphaGo actually won 4-1. So I was quite shocked. So in 2016, I was a graduate student, and I watched all the matches in the laboratory and realized that, oh, a new world or no new era has come. AI is really something. It will do something very impressive to the human history, and beating Lee et al. Is one of the sign of that. And actually, we're going to do very interesting things out of AI. As it turns out, AI applications are widespread nowadays, and it is actually very good in some cases. And for example, the recent GPT-3 model really understands the languages very well, quite well, and it can be used to model some applications that should understand the languages. So on and on and on. There are a lot of AI applications that is popping up these days, and they change our lives. And behind the scenes of this match between AlphaGo and E et al., there was some machines, a big machines that is consisting of a lot of computing units. So you can see that a lot of patterns are repeating here, right? So the same rack is the copy and pasted on and on and on. And inside this rack, also the same unit is copy and pasted on and on and on. And they are connected with networking solutions, basically. And the reason why there are a lot of redundancies or a lot of duplications of the resources is that in order to beat E et al., the AlphaGo need to do a lot of parallel searches, basically. And for parallel searches, these parallel machines will be very, very efficient. We just distribute the search job across a lot of machines, a lot of the same machines, basically. And it will result in the outcome much faster, about 100 times faster if you have 100 units of computing. So the version that the AlphaGo version that beat E et al. Was also a massively parallel machine, and 4 years later, now the machine behind AlphaGo, which is dubbed TPU or Tensor Processing Unit, it is becoming more and more parallel and more dense these days. So behind the scene of the era of AI, it is also the era of parallel machines. Parallelism everywhere. Okay, so now is the era of parallelism. So, as I said, we need more and more computations in order to prepare for the era of AI and IoT, etc., etc. So the trend is that computers are becoming more and more parallel. Here, parallel means a lot of things. So we have parallel resources, basically, and these resources can be CPUs, memories, I/O resources, or TPUs, GPUs, or neural processing units, or NPUs, or other FPGAs, or other kinds of resources. All those kind of resources are parallel, and they are parallelly deployed. So the reason why we need more parallelism in response to the more computation needs is basically two. The first reason is popping up about at 2005, which is the end of what is called Dennard scaling. So basically, what is meant by Dennard scaling is that we cannot increase the number of transistors for a fixed area of core. which means that we cannot increase the number of transistors for a single computing unit in a fixed area. So the reason is that the power consumption is constantly going up and up and up. So we cannot simply put more transistors inside the same core, basically computing units, and that is the reason why this end of linear scaling is we are fighting with the end of linear scaling with introducing multi-core systems. So we are basically introducing more and more cores basically. So at the beginning there were 2 cores. Instead of designing 5 gigahertz CPUs, we developed dual core systems, and then 4 core system, 8 core systems, and nowadays in 2020, even there are 16 core CPUs in desktop CPUs. And furthermore, there are even 64 core CPUs for server grade CPUs, and as far as I know, CPUs with 118 cores is being designed, and it will be delivered to the customers next year. So a lot of cores, a lot of densities are growing up in response to the end of linear scaling. You cannot just increase the gigahertz of the cores. You need to put more cores in order to utilize the number of transistors. Okay, so about 15 years, we have been so happy. So even though linear scaling ended, we can benefit from multi-core systems, and it is basically parallel resources of the cores, and we were good. And these days, we are facing a little bit different difficulties, which is the end of Moore's law. So it is basically saying that we cannot just increase the number of transistors for a fixed area. So the silicons or CPUs or something like some semiconductors are designed in a wafer that is basically a round materials that is consisting of the silicons basically, and we are going to just draw up some picture of the circuits to get CPUs and DRAM controllers and other semiconductors. So one of the main trend in the silicon industry is that we can constantly increase the number of transistors that can be put in a given amount of area. So that's the reason why we, for example, about 2 or 3 years later, we can get higher performance CPUs with almost the same price. So that's the reason. The reason is that we can just increase the number of transistors constantly. But we are facing almost the end of this Moore's law. So even though the lithography is becoming finer and finer, we cannot guarantee we cannot say for sure that the trend will continue in the future. So the number of transistors that can be put into a fixed area are no more increasing like a rocket. It is increasing, but at a very, very slow pace. So in order to deal with this problem, one of the main strategies is introducing what is called accelerators, which are specialized and extremely parallel hardware. So CPUs are very general purposes, so it can do almost everything, every computation we want to do. But accelerators are different. They do smaller subset of operations, but with a very higher efficiency. So it is specialized to specific workloads, but thanks to that, it can be extremely parallel and extremely efficient hardware. So GPUs are accelerators, and it is the most important types of accelerators. First, it was for graphics. Obviously, it is GPU, graphics processing units. But these days, GPUs are also specialized for AI applications and vision applications and other kinds of even data analysis applications, etc. And TPUs that was behind the scene of this AlphaGo was also a famous accelerator. And a lot of startups are trying to develop accelerators that is called NPUs, neural processing units, that are more specialized to AI applications. So these two trends, let's see these two trends. So the first trend, the end of general scaling, forces us to think about multi-core systems, basically parallel CPUs. And the second trend forces us to think of parallel resources of heterogeneous resources, not only CPUs, but also GPUs, NPUs, and TPUs, and even SSDs, FPGAs, etc., etc. So we are having abundance of parallel and heterogeneous resources these days, and in the future, the trend will continue. More and more parallelism will be introduced. More and more heterogeneity will be introduced to achieve higher performance, to meet the human demands for and more computations. Now the question is that, okay, now we have parallel resources. That's very good. We have parallel machines, parallel CPUs, parallel RAMs, parallel SSDs. Very good. But the question is how to coordinate those parallel resources that is coexisting in order to achieve higher performance. We need to somehow coordinate those parallel resources to collaborate rather than compete to achieve a single or unified goal of computing. That is what is expected from our human demands. For example, we want to compute AI graph using parallel resources, and they need to somehow coordinate in order to achieve that goal. How to do that? So usually it is widely known that it is a little bit difficult. It is a little bit difficult to achieve high performance out of parallel computing. In theory, parallel computing should work like this. So there are parallel dogs, basically. There are many dogs here, and they are eating the biscuits at the same time. In theory, they are working in parallel. But however, usually it is like this. They are competing for the same resources, and the three dogs here are competing for the same resources, and this resource is even not utilized at all, and they are doing well. But performance problems occur when some resources are contended or some resources are not utilized at all, blah blah. So in theory, we want this, but most of the time we cannot achieve this. We can achieve only the kind of chaos out of parallel resources. So let me explain why this happens and how to synchronize those parallel resources safely and efficiently. Okay, so let me introduce concurrency here. So parallelism is basically defined as multiple resources. If there are many resources, we can say that, there is a parallelism between these two resources or these many resources. And concurrency is about shared mutable states, and it is important. It is defined as shared mutable states or shared mutable resources, basically. So for example, CPUs, GPUs, memory, they are all shared among multiple processes. And server is shared among multiple processes or multiple virtual machines. Database is shared with multiple connections. Even data centers is shared among multiple users, basically. And all these resources are mutable, obviously. CPU is mutable. They can change their register values constantly, and database can be changed constantly, etc., etc. So parallelism and concurrency is defined this way: multiple resources and shared mutable resources. The problem is that shared mutable resources is the key to utilizing multiple resources. So you can think that parallelism without concurrency is not that interesting. For example, if resources are shared but it is immutable, then the resources are constants, and there is no difficult things that arises. So or there's no interesting things can arise. They are all constant. They are defined at the beginning, and it cannot be changed. So it is not that interesting in terms of the computations, basically. On the other hand, exclusive mutable resources are sequential, and there is no parallelism that is involved with these exclusive resources. We cannot share these resources, so there is no way to increase the performance using these resources, because it is specifically owned by a single agent, so it cannot be used in parallel. So in order to achieve high performance via parallelism, we really need to deal with concurrency, deal with shared mutable states. How to safely and efficiently use these concurrent shared mutable resources is the key to achieving high performance out of parallelism. Okay, so far we discussed that concurrency is fundamentally about shared mutable resources, and there is a trivial way to deal with concurrency. So shared mutable states are known to be difficult, and they are known to be all the sources of all the difficulty in the programming. But there is a trivial way to deal with concurrency. So it is basically at any moment, don't share any resources. And so that means that at any moment, if we can say that at any moment, a resource is owned by or used by only a single agent, then we can say that, even though resource can be shared, but at any moment the resource is exclusively owned by an agent, so there's no difficulty arising from the concurrency. It is nominally parallel because many agents can access this resource, but it is temporally not parallel because at any moment it is exclusively or owned by a single agent without parallel accesses. It is obviously safe because there's no difficulty or no problems arising from this shared mutable accesses, but usually it is inefficient because at any moment a resource cannot be shared at all. It can be, it can be time multiplexed, but it cannot be used at the same time. So that's the reason why it can be inefficient. On the other hand, what we really want to achieve is a scalable concurrency. That is actually accessing resources at the same time. So for example, we want to design a job queue, a concurrent job queue, supporting, for example, 1 million operations per second. So in the real world, such systems are deployed in the name of, for example, Redis or RabbitMQ, blah, blah. So this RabbitMQ, for example, is a job queue, and if a web server is wanting to request for a job to be done, it just throws the job to the job queue, and this job queue is constantly pulled by workers, and a worker is getting a job out of this queue and executing the job. And we have a lot of concurrent connections at the same time, such as a queue must be as fast as possible. That's the reason why we want the concurrent job queues can support, for example, 1 million operations per second. That is usually this is similar to the number of concurrent connections that can be handled by a single server in these days. So for this scalable concurrency, multiple agents actually can access the same job queue at the same time. So in that sense, it is truly shared mutable resources. It is shared among, for example, 1 million handles, and it is mutable because jobs can be added or removed from the queue. And in order to support this kind of actually scalable concurrency, so the problem is that it is usually difficult to reason about. It is definitely efficient. As I said, it can support many operations per second, but usually this kind of scalable concurrency is a bit difficult to reason about, especially for their safety and correctness. How to ensure the correctness of the queue, which means it actually acts like a queue, in the presence of shared mutable accesses. So it is difficult usually. So let me explain why it is difficult. So the essence of this difficulty there is nondeterminism. So concurrency is difficult because it introduces combinatorially explosive nondeterminism. So combinatorially explosive basically means lots of nondeterminism. So we don't need to worry about these difficult words. So the first source of nondeterminism is usually called interleaving. So let's say that there is two threads. This is x equals 1 is a thread, and x equals 2 is also a thread. Let's assume that. And the problem is that depending on the order of the execution of these threads, the end memory is 1 or 2, depending on the order of the execution. If x equals 1 is executed before x equals 2, then the end memory should be x equals 2. On the other hand, if x equals 2 is executed before this thread x equals 1, the end memory should be x equals 1. So these kind of possibilities this kind of the number of interleavings are basically it corresponds to the factorial of the number of instructions basically. That is combinatorially explosive basically. The second, which means that if there are a lot of threads or if there are a lot of instructions inside a single thread, then the number of possibilities of interleavings are going very high. So in this example, we only have 2 interleavings, but if we have many threads and many instructions, it will easily go higher than millions and billions and zillions of cases. And the second sources of nondeterminism is optimization by hardware and compiler. For example, let's look at this code. There are 2 threads, and let's assume that this A and B, which is in the small case letters, are registers, and this X and Y, which are big case letters, are shared memory locations. And let's assume that X and Y equals to 0 at the beginning of the execution. And in the left thread, the thread is writing 1 to X and then reading from Y. On the other hand, the right thread writes 1 to Y and then reads from X. And the question here is that, is it possible to observe A equals B equals 0 in the modern hardware? So surprisingly, it is okay. It is observable in actual hardware, even though you can naively think that either x equals 1 or y equals 1 should be executed first. And if x equals 1 is executed first, then b should be 1. In other case, y equals 1 should be executed first, then this should be reading 1. So you may naively think that. But this reasoning is broken in the presence of optimizations. And in particular, if reordering is happening in the left thread or right thread, x equals b equals 0 can be possible. So let's say that hardware or compiler is smart enough to deduce that two instructions in the left thread are not dependent on each other. So it may execute the second instruction first, reading from y first. In the same reason, the compiler or hardware may deduce that these two instructions are independent with each other. So maybe the thread is executing the read from x first before writing 1 to y. So if it is the case, it can be the case that a and b are 0 at the same time, because they are reordered and they are executed before the earlier writes. So this kind of optimization and this kind of additional non-determinism is happening. It's really happening in the hardware and it's really happening in the compilers. So we need to somehow deal with this, and we need to somehow learn how to defeat this kind of non-determinism. So this is basically the topic of this course. The entire course is devoted to understanding concurrency and understanding the non-determinism that is arising from concurrency. And furthermore, we want to tame this non-determinism to make sure that this non-determinism is actually beneficial for our purposes. So there are basically two approaches to taming non-determinism. The first approach is about API. So we are going to enclose the non-determinism within a safe API. So let's think of a lock or conditional variable or threads or other kinds of abstractions that is present in the operating system's implementations and other kinds of systems programming. For example, the lock, it has a very simple API. You can acquire a lock, you can release a lock, and that's all. And there is no things like interleaving of instructions. Interleaving of instructions inside the implementation of the locks. It is no longer of our interest. What is needed to use a lock is the specifications of the lock. The specification of the lock is that two threads cannot acquire a lock at the same time. So only a lock is held by a single agent. That is the specification of a lock. Conditional variable has its own API, and other kinds of concurrent objects like concurrent data structures or concurrent garbage collectors, they all have safe API. So one needs to know the safe API and how to use it safely instead of understanding all the implementation details of the APIs. So that's all the implementation details of the concurrent objects. That's basically the one of the most important approaches to taming non-determinism. Once non-determinism is enclosed within safe API, we can just forget about the implementations. We can use the concurrent objects using only the APIs. So let's think of another example. Let's think of a concurrent stack. That is a stack, but that is concurrent, so that multiple threads can access the stack at the same time. So it is such a stack. So the concurrent stack API should hide two low-level non-determinism. So for example, inside the implementation of the stack, it will consist a lot of instructions, a lot of, for example, x86 instructions, and they can be reordered and they can be interleaved. But we no longer are interested in such low-level non-determinism. So because API will enclose such low-level things, and on the other hand, we only want to know the higher level non-determinisms that is exposed by the API. For example, if two threads are trying to push values to the same concurrent stack, then there will be interleaving of the operations. Either a thread A is pushing a value first, or a thread B is pushing a value first. So, but it is an intended parallelism, intended non-determinism. We want to enjoy the performance benefits that is allowed by the kind of non-determinism. So that's the reason why we usually want to expose a high-level non-determinism to the programmers. Okay, that is basically the first approach to taming non-determinism. And the second approach to taming non-determinism is about implementation. Okay, if we know safe API, we can just ignore the implementations. But someone needs to implement in order to satisfy the safe API. And what should they do for actually implementing such concurrent objects? And the key idea here, or key approaches here, is that we only use a well-studied synchronization patterns instead of using arbitrary code. We just write down a very well-established synchronization patterns. So for example, locks are using what is called release-acquired synchronization, and what is called DQ, concurrent DQ, work-stealing DQ data structures is using what is called a fence synchronization. So there are a few synchronization patterns that can be combined in order to achieve necessary or desired coordination of the desired synchronization. And we are going to learn such synchronization patterns that will be necessary in the implementation. What is fortunate about this is that we only need to know about 2 or 3 synchronization patterns. So that's all. We don't need to learn thousands of synchronization patterns because there are only a few synchronization patterns. So in this course, we are going to learn these 2 aspects. What is the safe API of existing concurrency library? For example, locks and conditional variables and concurrent stacks and concurrent work-stealing queues, blah blah. And also we are going to learn the implementation of concurrent libraries, how to implement such locks, how to implement conditional variables, how to implement concurrent stacks and queues, etc. Or how to implement concurrent garbage collectors. That is the main topic of this course basically. Okay, so I said that we are going to study API and implementation of concurrent libraries. And I observed that there are 2 layers of concurrency. Basically, one is easy and the other is difficult. One is the easy one is usually called lock-based concurrency, which I called trivial concurrency in the previous slide. And that means that lock basically mandates that at a moment, a resource should be owned by a single agent. So it removes all the parallelism for single resources. But it may be the case that we have multiple resources that is protected by their own locks, and in that case, multiple resources can be accessed at the same time. So it is the case that lock-based concurrency removes parallelism, but for some cases, it may be sufficient for our performance target. So that's the reason why we are learning lock-based easy concurrency. So we're going to learn threads, locks, conditional variables, or other things that is relevant to lock-based concurrency. And the benefit of this is that it is very simple, because we remove a lot of parallelism. We no longer need to think about non-determinism at all, because there is no such non-determinism. It is very simple. But because we removed a lot of nondeterminism, maybe it is the case that it has a very low scalability. So it may be the case if we acquire a lock for a lot of a big resource. So if we protect a big resource with a lock, then it may be the case that the big resource can be accessed only at one at a time. So that's the reason why we may proceed to the lock-free concurrency or difficult concurrency or daring concurrency that is usually called by some authors in the research community. And the lock-free concurrency is not going to use locks basically, and instead it will allow concurrent accesses at the same time, actually allowing concurrent accesses to the same object at the same time. So in order to tame the nondeterminism that is arising from this lock-free concurrency, we will learn theory and tools and practice of this lock-free concurrency. And the theory will be semantics and reasoning principles that is characterizing the nondeterminism basically. And tools will be synchronization patterns, the building blocks for lock-free concurrency. As I said, there are only a few synchronization patterns. That is a good thing. So we need to only learn a few synchronization patterns. And also we will learn a little bit practice of lock-free concurrency. See, API and implementation of actual lock-free objects like data structures, like stacks and queues and lists and etc. etc. So we are going to learn such things. And furthermore, a little bit more about practice is that we're going to learn a little bit about garbage collector, basically. Okay, so far is the introduction of what is going to be learned during this course. So to summarize, we are going to learn the API implementation of concurrent libraries. And these concurrent libraries can be usually classified into two categories, easy one and the difficult one. So we are going to deal with both of them. We are going to deal with easy ones, API and implementation of the easy ones, and API implementation of the difficult ones at the same time. Here are a few general advices for concurrent programming that can be applied to most of the situations when you're going to do concurrent programs. So if this course is too long, just memorize these things. And the first advice is always start with a easy concurrency. Always use locks and always protect your resources with locks when you are going to deal with shared immutable states at the beginning. And only when it is a bottleneck, and only when the locks introduce a lot of bottlenecks here, you should go to the difficult concurrency. If easy concurrency is just enough, just use it because it is much simpler and easier to reason about. There is a very famous wording by Knuth, which is premature optimization is the root of all evil. So don't optimize things prematurely. Just start with easy concurrency. The second advice is about difficult concurrency, and it is actually not that difficult once you understand the theory. So if you understand the fundamentals and if you understand the theory, applying it to the difficult concurrency is systematic. You don't need to worry about the magical things. So that's the reason why if you understand the theory, it is no longer very much difficult. But the other side of the story is that I have to confess that understanding the theory may be a little bit difficult and it requires some disciplined study, which is the aim of these courses. And the key of the difficult concurrency is taming the right amount of nondeterminism. You should not remove too much nondeterminism because it will introduce scalability problem. But at the same time, you should not remove too less nondeterminism because it will introduce correctness problems. So in order to achieve scalability and correctness at the same time, you need to remove or tame the right amount of nondeterminism. So that's the key criteria for this difficult concurrency. The third aspect of this advice is that probably your code for your concurrent code is not that big. because most of the things can be done in a sequential way. So concurrency is usually done for a very highly concurrent, highly accessed code resources, and it is usually small, and it is usually simple. So there will be not so much to code, but you have to know that there is much to debug. So it is really easy to introduce a bug inside your code in concurrent programs. It is much more easier than sequential programs. That's the reason why debugging is most important activities in concurrent programming. But fortunately, we have a lot of tools that support us in debugging. Sanitizers, stress testers, assertions, and line-by-line debugging, etc. So you're going to learn how to use those tools in debugging your concurrent programs. And furthermore, mathematical and PL thinking helps a lot in debugging such things because they mandate us to think about, pedantically think about the safety of the programs. And in the mind of proving the correctness of a program, we need to deal with all the corner cases, and we need to think of all the corner cases in the course. So that's the reason why it will help us to debug the code. So I imagine that it is this course is for senior, and most of you already took courses in PL, but it is not required for this course. But it is much easier for you to already take a PL for taking this course. Okay, this is pretty much end of this talk, and this is pretty much the end of the first day. And I hope you will continue to register this course so that you will learn concurrency in the remaining of this semester. And I hope this course will be very fun and also deep at the same time.